We'll now develop an expression for the pitching moment on a thin airfoil. On the right, I have the expression for gamma as a function of, this is our Fourier sine series as a function of theta. And then remember, in order for these to satisfy the thin airfoil theory, the fundamental equation, this is the value for A0 and AN. These are the Fourier coefficients here that then will satisfy that equation. And here I've copied down the small angle of attack version. That's what we're going to include here. This is the traditional development of the pitching moment, which includes small angles of attack. Okay, so first let's just draw a picture of this airfoil. What we're trying to find is the pitching moment about the leading edge. And we've got some airfoil with a camber line that looks like that. And we'd like to find the pitching moment right there at the leading edge. And if we integrate over this dx naught, this is x and y. If we integrate across this chord, and then just look at the normal force, so this would be a differential normal force, then we can integrate that and figure out what the pitching moment would be at the leading edge. So first of all, let's look at that differential normal force. The differential normal force through small angle approximation, through small angle of attack approximation is equal to or very nearly the differential lift. And the lift, we know from the Kutta-Joukowski theorem that that can be written as rho v infinity. Since we're just looking at the differential section of lift, it would be differential of capital gamma, which in our case would be rho v infinity gamma of x naught times dx naught. Okay, so a differential normal component here is equal to the differential lift component according to small angle or small angle of attack, and then using Kutta-Joukowski theorem we get here, and we just are swapping out now the strength of our vortex sheet there for that d gamma. Okay, so let's now write an equation for the moment about the leading edge is going to be equal to minus rho v infinity. What I'm doing is I'm bringing down these guys right here, and then we're going to integrate that gamma term from x naught equals 0 to the chord, across the whole chord, of gamma x of x naught times x naught. So we're going to take its local position multiplied by gamma of x naught to get the moment arm of the pitching of the lift that is now going to create that pitching moment. And we're going to integrate over dx naught. Okay, so let's use a change of variables here into theta instead of x, and we get negative rho v infinity times c squared over 4, because we've got a c over 2. We've got 2 of those inside the integrand there. So when we do that change of variables, then we've got the c squared over 4. Let me just write down that change of variables here off to the side so remember what that is. So it's x is equal to c over 2 times 1 minus cosine of theta. So we're swapping out all of the x's for thetas, and the dx, we can differentiate that, and we get c over 2 times sine of theta d theta. Okay, so that's all we're doing, is we're using this change of variables here and plugging it into here to get this equation down here. Okay, so we now have the integral, and remember our bounds of integration changed into theta from 0 to pi. And now we're going to have gamma of theta naught times 1 minus cosine theta naught sine theta naught d theta naught. Okay, so this sine theta naught comes from that guy right there, and the x naught term here becomes this 1 minus cosine theta from the change of variables. All right, so our next task is to plug in this equation for gamma of theta naught. So we know, or we can put in an infinite series solution in there for gamma, and put it in terms of the Fourier coefficients of that series. And so once we do that, the pitching moment at the leading edge, it can now be written as minus rho v infinity squared c squared over 2 times, and now I'm putting in that first term of that infinite series. So a0, and then we're going to integrate from theta naught equals 0 up to pi. And now I'm taking this term here and multiplying it by the 1 minus cosine theta here. So what we're going to get, so we've got a 1 plus cosine theta and a 1 minus cosine theta. This one's multiplied by sine of theta naught, which when we evaluate gamma at theta naught, that gives us a sine theta naught in the denominator. So these two sines will cancel out, and we're left with 1 minus cosine times 1 plus cosine. So we can, let's see, so we'll get 1 plus cosine theta naught times 1 minus cosine theta naught d theta naught. Okay, so that takes care of this first term here, and now we're going to take the second term and plug it in here and multiply it by these guys here. So what we get there is, and I'm going to move the integrand inside of the summation, so n equals 1 up to infinity of a sub n times the integral of theta 0 equals 0 up to pi. And we get 1 minus cosine theta naught times sine of theta naught. And then we've got a sine n theta naught here that needs to come down. So that's going to be sine of n theta naught d theta naught. Okay, so that is our, that's kind of a big equation, but we're going to find that it simplifies quite a bit. So it turns out that the integral of this term right there is simply pi halves. So that's kind of nice when we integrate that from 0 to pi. And then we find that on the right-hand side, first we've got this, we can distribute this. So we've got 1 times this stuff and then cosine theta times that stuff. So when we do the 1 times that, these terms here give us pi halves for n equals 1 and 0 for n not equal to 1. So that's nice. And then when we do the cosine theta naught times sine theta naught times sine n of theta naught, it turns out that that gives us pi fourths for n equals 2 and 0 for n not equal to 2. So that simplifies this solution significantly. So let's plug these things back in now. And what we're going to get is minus rho v infinity squared c squared over 2 times a0 pi halves plus, now we've got two different terms over here on the right hand side. We're going to have, for n equals 1 we're going to get pi halves, and for n equals 2 we're going to get pi fourths. So that gives us a1 times pi halves minus A2 times pi fourths. Remember that negative sign up there. That needs to come down for the A2 term. Okay, so I'm just going to simplify this a little bit further and say this is equal to minus pi times rho. I bring that pi out front. Rho v infinity squared c squared over 4. So I'm bringing a 2 out as well. And that is multiplied by a0 plus a1 minus a2 over 2. Okay, now let's make this non-dimensional. So remember that's the dimensional moment at the leading edge per unit span. It's the section moment. So let's look at the coefficient of moment at the leading edge, and that is equal to the moment at the leading edge divided by 1/2 rho v infinity squared c squared. That's how we non-dimensionalize a section moment. And so when we do that, we get minus pi halves a0 plus a1 minus a2 over 2. Okay. Now, just a little note over here. We're going to swap out a0 for the lift coefficient. We could go back to the development of the lift coefficient, and the lift was a function of a0 and a1. And so we can solve for a0 from that equation, and a0 is equal to the lift coefficient divided by 2 pi minus a1 over 2. So if we plug that in now for a0, we can rewrite the pitching moment coefficient about the leading edge as minus pi halves times CL over 2 pi, and then we've got a minus a1 half and plus a1 here, so that will be a plus a1 over 2, and then minus a2 over 2. Okay, and so then this can simplify one step further. If I multiply this pi halves through, then what I get is minus CL over 4 plus pi over 4 times A2 minus A1. Okay, so we've simplified this down quite a bit, and now so this is the pitching moment at the leading edge, and I'd like to write this. I'd like to pull down the A2 and the A1 now, because those are just coefficients in our Fourier series, which we know from up here we can compute A2 and A1. And so A1, for example, is just going to be 2 pi dyc, and then we have a 1 inside of here. A2 is just going to have a 2 inside of here. So we can simplify that down actually and write that the pitching moment at the leading edge is equal to minus CL over 4 plus 1/2 times the integral of theta equals 0 to pi dyc dx times cosine of 2 theta minus the cosine of theta d theta. Okay, and that is the equation for the pitching moment about the leading edge. So what we've done is we now have an estimate for the pitching moment at the leading edge. It depends on the lift coefficient, which we can get from thin airfoil theory, and then it also has this constant back here that depends on when I say constant, I mean constant. It's independent of angle of attack. This term right here depends only on the slope of the camber line. We're going to integrate that over the entire chord, and then once we've done that, this is just a constant that then can be added to the lift coefficient at any angle of attack, in order to get the pitching moment at the leading edge. So let's take this one step further, because there's something very interesting that comes out of thin airfoil theory that comes from this pitching moment equation. So let's look at the aerodynamic center. The definition of the aerodynamic center is that it is the point on the airfoil where the pitching moment is invariant with angle of attack. So let's draw an airfoil here that's from thin airfoil theory. And we've got some camber line. And what we know right now is the pitching moment at the leading edge. And we want to find the point. Now, from thin airfoil theory, we basically assumed that camber line collapsed along the chord line there. And we're still taking into account the slope of that camber line at every location, but the mathematics that's built into this are assumed that that camber line was coincident with or very close to the chord, so that we could treat it as a panel instead of as a sheet of vorticity. Okay, so that helped us simplify the mathematics a little bit. So we're looking for the point along the chord line here where the pitching moment is invariant with angle of attack. So I'm going to say that that's going to be the pitching moment at the aerodynamic center, where we don't know where that is right now. But we can write an equation for the pitching moment at the aerodynamic center. It's going to be equal to the pitching moment at the leading edge. And then remember, we have some normal force, which is equivalent to lift according to the small angle approximation. The normal force is roughly equal to the lift. And so the pitching moment at the aerodynamic center then is going to be the pitching moment at the leading edge plus the lift coefficient times xac over c. So we don't know where the aerodynamic center is right now, but if I'd have to multiply xac over c, so some fraction of the chord, times the lift coefficient to move that force over to the from the leading edge to the aerodynamic center to account for the pitching moment that force is creating at the aerodynamic center. Okay, so now we can apply the definition of the aerodynamic center. We can take the derivative of the at the pitching moment at the aerodynamic center with respect to alpha, and that would give us the change in pitching moment at the leading edge with respect to alpha, plus the change in lift coefficient. All of these are section with respect to alpha times xac over c. Okay, and by definition, this needs to equal 0 in order for it to be for xac over c to be the aerodynamic center. Okay, so let's take the derivative of the pitching moment equation that we have right up over here. Let's take the derivative of this with respect to alpha. So when we do that, we get minus CL alpha. Let's see, we're going to have minus CL alpha, where that's the derivative of CL with respect to alpha, divided by 4. And then the second term over here is independent of alpha. So when we take the derivative of this with respect to alpha, that disappears. So then the next term here is just the change in CL with alpha, which is CL alpha times xac over c equals 0. Okay, so CL alpha actually is going to drop out here. We can divide both sides by that and set the final two terms equal to each other, and that tells us that xac over c is equal to 1/4, meaning that the aerodynamic center is at the quarter chord of a thin airfoil. This is a very important thing that we learned from thin airfoil theory is that most airfoils have an aerodynamic center very near the quarter-chord. And we'll find from experimental data and from other numerical methods that holds true, that it is always very near the quarter-chord, and that estimate comes from thin airfoil theory. One last thing we'd like to do is look at the pitching moment at the quarter-chord or the aerodynamic center. See, we've shown that the aerodynamic center from thin airfoil theory is at the quarter-chord, and now we'd like to know what the pitching moment coefficient is at the quarter-chord. So we can do that by taking this equation up here. This is the pitching moment about the leading edge, plugging it in here, and then adding CL over XAC over C, which is 1/4. So CL over 1/4. And so once we do that, we see we actually have a minus CL over 4 here, plus this term here. And so it turns out that those CL over 4 will cancel. And so what we'll get here from these two equations is that the pitching moment at the quarter-chord, C over 4, is equal to simply this constant right here, 1/2 the integral from theta equals 0 to pi of dyc dx cosine of 2 theta minus cosine of theta d theta. Okay, so that's the pitching moment at the aerodynamic center or the quarter-chord of a thin airfoil.